we have begun, and I start okay, so here we go. And the thing that we were talking about was let's see, just need to set this up. There we go. All right. So, the thing that we were talking about was this very interesting result that we had for the refractive index. Okay. And so everyone can see clearly now? We're all set here? Yeah, just give me a yay and
yes.
Yes, okay, cool. So we have this refractive index, and for the first time we have the concept of resonance, and with this new equation for the refractive index, we found some unexpected interesting successes of the Lorentz model. We found that now there is we found that metals are, what we found is basically that for plasmas, okay, and a metal is a plasma and so is the ionosphere. The ionosphere is an extremely dilute plasma, and a metal is a more concentrated form of a plasma, but in the end, a plasma is always a collection of mostly free charged particles. That's what a plasma is. And so what we found is that then this new equation for the refractive index can be written in this form. You can define a plasma frequency, and if your incident wavelength happens to have a frequency which is more than the plasma frequency, then the refractive index is real. Okay, this quantity is less than 1 and the whole thing is real. And so then, because the refractive index is real, that means that the wave propagates through the material, okay, as usual. But the interesting situation happens when your incident frequency is less than the plasma frequency, in which case the refractive index becomes purely imaginary. We already have seen how a pure imaginary refractive index, that's the imaginary part, results in absorption, right? Because there's an I which couples with the e to the I in the propagating phase there. And so we've seen how that results in absorption, okay? And so a pure imaginary refractive index means strong absorption. That's the only thing going on. And that means that metals are very strongly absorbing in the visible frequencies, because the plasma frequency for copper, for example, works out to be more than the visible frequencies. So the visible frequencies are less than the plasma frequency, and therefore visible frequencies are strongly absorbed. I asked you to accept the fact that if a material is strongly absorbing for some certain frequencies, then it is also strongly reflecting for those frequencies. In the 600 level course, we prove that it falls right out of Maxwell's equations, because on the face of it, they're not related. And they even sound a bit counterintuitive. That, what do you mean? Something which is strongly absorbing at a certain frequency, why would it be strongly reflecting at that? One's a bulk property, that's the absorption. The other is a surface property, reflection. So what's the connection? And we don't have the math to be able to prove it, but I will use a demo to at least show that, what that means. Okay, so metals are transparent to UV, which happens to have a higher frequency than the plasma frequency. And these are facts, right? Now, the other thing was that, for the ionosphere, let's just wrap that up too, and then I'll show you the demo quickly. For the ionosphere, what we have learned, so this is actually the starting point also for today, which is 0505. Oh, what's this? 30, look at that, 2020. So what we said is for the ionosphere, the plasma frequency is 9 megahertz. And so you see how 9 megahertz sits between the FM band, which is 100 megahertz, and the AM band, which is used for long distance communication, which is less than a megahertz. So what's the idea there? The idea again is that you can work out the new plasma for the ionosphere. So new plasma is, of course, all this, 1 over 2 pi, it's this formula. So square root, and what is the N? Now, for copper, the number density was 10 to the 29 per cubic meter. For the ionosphere, it's a lot smaller, 10 to the 12 per cubic meter, but then everything else is the same. The E, the charge, E squared, and then the mass of the electron. That's what went in there. And then epsilon naught is, of course, a constant, 8.85 times 10 to the minus 12 SI units, right? And so you work this out. And of course, I've given you the result already, that this works out to 9 megahertz. Okay? So that was 3 times 10 to the 15 hertz, and this is 9 times 10 to the 6 hertz. So it's all because of that number density. And so, what that means is that the FM band, transmits through, but the AM band is strongly absorbed. And once again, strongly absorbed means strongly reflected. Okay, so how does that help in long distance communication? It's quite neat. So here's a radio station, let's say, blaring out signals. Let's say, so if it's a FM, let's say, FM comes out there, and it just goes right through the ionosphere and out. Okay, and it's sort of lost. So only if you are in direct communication, like direct line of sight. So here's another station, and you can go direct to it, and that works. But if you are not directly aimed at the other one, then FM, if it goes anywhere else, it just goes out and escapes. On the other hand, AM, so here's AM, right? Yeah, and just if you have any questions, just holler forth. Okay. The AM band, on the other hand, cannot propagate because it is strongly reflected, and because it's reflected, it can go like this, right? And so now here you have another station on the far end, and you see that this now can go over there. So AM, you can do long distance. Okay, but not with FM. Okay, so that's the idea. Now, I've been continually saying that strong absorbers are strong reflectors. So let me just try and prove that with a demo. And also, the demo, it's more like what do I exactly mean by that? So this is strong absorbers at a certain . Because this is a remarkable thing. It comes right out of Maxwell's equations. At a certain frequency nu are also strong reflectors at nu. Okay? So what does this mean? So first of all, what it means, I'm not telling you the why, but what it means is that, let's say that here's this material. Okay, so here's this material. And let's say that you are inside this material already, right? So let's say you're here and this is an electromagnetic wave trying to propagate through. Okay, so if you are a strong absorber, what it means is that the electromagnetic wave inside the medium, inside the highly absorbing medium, well, I mean, as it suggests, gets strongly absorbed. Okay, so that's all that's saying, that as it's trying to propagate, it's getting strongly absorbed. But a totally different question is the fact that if you are coming in from the outside, so the electromagnetic wave is now incident on this medium, how much of it actually made it in the first place? Okay, so the question is that the electromagnetic wave incident on the medium, okay, on a strongly absorbing medium, electromagnetic wave, whoops, I'll correct this later, but for now, electromagnetic wave incident on strongly absorbing medium, and so it's incident, so it's coming in from the outside, okay? How much of it actually gets in the first place? And it turns out that most of it gets reflected. Most gets reflected. This is an amazing fact that most of it gets reflected. Whatever leaks in gets strongly absorbed. Okay? Now, why does that happen? And there's this, you could almost sense a bit of a philosophical implication to this really amazing fact of nature, that it's almost like, this material medium, this is a good way for the medium to preserve itself. Meaning, if it's a highly absorbing, if it highly absorbs some radiation of some frequency, then, if it lets it all in, then it might absorb too much and might get denatured or unstable or damaged thermally or whatever. So its defense mechanism is that most of it just reflects. And then whatever comes in gets strongly absorbed. Okay? Now, why does this happen? We can't prove that here, but I will show you what I mean by it. So now this demo is not quite as spectacular as what we could have done in class. So, I'm sorry about that. But here's, so what I'm going to do is, so here's a red transparency pen. And actually in this case, I would appreciate it if, and I'm not sure how, if there was some indication of whether you are getting what I'm trying to show you. Okay, so what you see, especially, so let me tell you what I'm trying to show you. So here's a red pen, right? And it has red dye in it, right? And so it won't be surprising to you. So now I have a little cuvette here with some water at the, actually, let me ask this question. Do you see water right at the bottom of the cuvette? a little hard to see, I suppose, but there. Do you see the water?
I can see it.
Yeah,
Okay.
I can see it.
Yeah, there's a little water, right? And so I'm opening it. And obviously, if I dip the pen in it, then, I expect to see it's red dye. So there you go. It becomes red. Okay. So, I mean, this is not surprising that it's red dye. And so and so it's red, right? What you see is red. And, remember what you're actually, okay, well, what you see is red, right? And what it means when we say we're seeing red is that, and I feel like I have to draw this, that, here's the cuvette. Okay. And, there is this material inside. So the dye mixed in water. And what happens is that when we are looking at it, then, light's coming in from the, there's light coming in, white light. And what's happening here is that the greens and the blues are getting absorbed by the dye, right? And so when that happens, then so the greens are absorbed, and so here's your eye. Okay, so greens are absorbed, and so what comes through, it's the reds, right? So you see the red. Now, if this red dye is good at absorbing the greens, then it should be a good reflector of green, right? And so tell me, I mean, so what do you see here? Like, what kind of color do you see? So this is, what I did is I took this surface, a black plastic surface, and then I took the red pen, right? And I started, basically I want to just, I'm putting down the red dye on this black substrate, okay? And do you see a greenish sort of tinge to the reflection?
Yeah.
Yeah?
Yeah.
So, I mean, and this is something that if someone has seen dried up ink on, like if in the good old days people used ink wells, and right where the cap would fit on the ink well, there was a lot of dried up dye, and so it's easy to see when there's concentrated dried dye. But you see how it reflects in the green, which means it absorbs in the green, and that's why when you look in transmission, you see just the reds coming through. Okay, now there's a more spectacular demo with laser dye, because laser dye, and I used to borrow some from Richin for this purpose, the orange looking dye in that she uses in her dye lasers. If you put it in the cuvette and mix it in with methanol, and you look, you do this experiment here, look through, then you will see a very dark red. This is not as dark red, but you'll see a very dark red. And that's because it's good at absorbing the greens. In fact, that dye is spectacular at absorbing the greens. And so the nice thing about that dye, that was a spectacular demo, was that if I put a little bit of the dye powder onto a surface and, you look at it, just on, because, the thing is that with the dye, there's lots of fine grains. Also here, I mean, what's happening is that it's drying out, and there's a lot of fine grains of the dye. And these grains, there's a lot of surface area, and so there's a lot of reflection. And the dye, especially, and I don't know if Scott or, um, well, I guess Scott's the only guy who's worked with Birchin in our class. Um, but I don't know if Scott's ever looked at the dry dye particles laid out on a surface. Uh, they look a brilliant green in color, very dark, rich, brilliant green, which means that they are very good reflectors in the green, which also means they're excellent absorbers in the green, and that's why you pump that dye with argon ion light, with the argon laser, which is a green laser. You know, so this is a remarkable fact of nature, that it's almost like a protection mechanism that materials have. That if they are extremely strongly absorbing in a certain frequency, then they'll also just reject most of that light at the outset, so that not a whole lot gets in. Um, any questions about this? So I'm actually relying on a slightly lamer version of a demo, um, you know, to make a point here, a physics point, which is a rigorously provable mathematical thing, but I don't have the math sort of to pull it off here. So this is why, when I say, if I can show you that something is a strong absorber, then automatically I can infer that it's a strong reflector too at that frequency. Okay? Any questions? So now it's also at this point we can understand something else which is interesting, which is this business of the blue sky and the pink sunset. Okay, so let's get to that. So we're learning some nice. So actually, let me just write in here that so there's this, but then when you view dye particles by themselves, fine grain offer lots of surface area for lots of reflection. Sorry for all the folksiness here. Lots of reflection. You see that the dye appears green, and with the laser dye it's a brilliant green, a very rich green. Here's green in reflection. Okay, so, and meanwhile this was in solution, dye appears red in transmission. Okay, so hopefully this point is made. Okay, so now let's look at the blue sky and the pink sunset, and I'm sort of just jumping a little bit ahead. So let me see if I can pull it off by and I think I can. Normally it appears a little later in the scheme of things, but so this was another, it's continuing this theme of more like um, success of Lorentz model. And in fact, I think, I'm not sure where I read this, but partly Lorentz was interested in answering this specific question about the blue sky and the pink sunset. And it was hailed as a sort of a good, like a big proof or something, a big success of the Lorentz model that he was able to explain this. Okay. We've already discussed that the blue sky is due to scattering by air molecules. Okay, and actually both of this, blue sky and pink sunset, scattering by air molecules. So this is the Rayleigh scattering, which is defined as that the scatter size is much, much smaller than lambda, the optical wavelength, right? So, okay, now before we look at that, there is one other piece of EM that I'm just going to introduce, and it's an important, I mean, like when you take an advanced course in EM, look for the proof of the answer to this question, that how are electromagnetic waves produced? Any electromagnetic wave of any kind, anywhere, how is it produced? There's only one mechanism by which electromagnetic waves are produced. Does anyone know? By the way, because it's a three-word answer. Does anyone know how all electromagnetic waves everywhere in the universe, there's only one mechanism for producing them? Does anyone know that? Know what it is? What needs to happen for an electromagnetic wave to be produced? I'll count to 10, to 5, because if someone would have known, they might have said something. I'll count to 5, give you a chance to hazard a guess or something. No guesses? I mean, you could have said, for example, there's spontaneous emission, there's stimulated emission, so an atom jumping from a excited state to a ground state, and that would have been a valid answer. Classically speaking, this is a classical course, after all. Classically speaking, for an electromagnetic wave to be produced, there has to be a charge being accelerated. Okay, so accelerated charges, that's what you need. I mean, X-rays come from decelerated charges, as you know, but accelerated charges, that's where electromagnetic waves come from in the form of radiation. Accelerated charges radiate. That's where radiation or electromagnetic waves that propagate, that's where it comes from. So now that means in our Lorentz model, so you have your electron going back and forth, right? I mean, so there's this electric field making it, pulling it back and forth, back and forth. So it's actually being accelerated back and forth. So it will radiate, right? So in the Lorentz model, I can, I've written out what this displacement looks like, and the acceleration is just double dot, right, of that. So the displacement, we already solved it. What did we say it was? We said, here it is. the displacement for the electron is E over m, polarization, E naught, e to the, if the atom is located at the origin, there you go, right? So we already wrote that out. And so, I mean, the point is that the important point is, because we'll see now what we're going to see in the next line is that for Rayleigh scattering, you know that the scattering is proportional to the fourth power of the frequency. Everyone, you know, and that's why blue scatters most, and so that's what you see, the blue sky, right? Well, it's going to come out now from here, because when you take the double derivative with respect to time, you'll notice that this is the only thing that depends on time, right? So the double derivative, I mean, only acts on that. And so you notice that this gives you, and twice meaning minus I omega squared, right? And then the whole thing back, right? So that's what you get. And so you notice that this is equal to minus omega squared x. And so that's the acceleration. And we just said that the power radiated by this accelerating electron, well, it's going to be proportional to its acceleration. So it's going to be proportional to omega squared, but I should have, in fact, I should make that change here, that the field radiated. This is the electric field radiated by this accelerating electron is proportional to the acceleration, proportional to omega squared, which implies the intensity or power radiated is proportional to, E squared, which means proportional to omega fourth. Here you go. Okay, and that is the signature of Rayleigh scattering. Okay, so the point is that Lorentz was able to very simply see the origin of Rayleigh scattering. Okay, and of course, then if you put in the numbers, then blue is omega is equal to 2 pi c over lambda, right? And lambda for blue is 400 nanometers or so. 400 nanometers. So anyway, this works out to 8 times 10 to the 14 per second. That's omega. And for red, the same thing leads to 4 times 10 to the 14 per second. So you can see that blue, I mean, that's a factor 2, but then to the fourth. So blue scatters factor 16 times more strongly. That's more than an order of magnitude than red. Okay. So this is a success for the Lorentz model and Rayleigh scattering. One thing that, what about the pink sunset though? And with the pink sunset, you've noticed that the light is not that spread across the sky. It's pink right near where the sun is, right around the sun. It's pink. And there's still residual of blue all around, and the blue just gets fainter and fainter. Okay, and then maybe right at the end, all you see is the pink where the sun is. It's kind of localized near where the sun is. There's an interesting reason for all that. So, I mean, let me just explain it with a diagram here. So here's this Earth, and then the atmosphere of the Earth, right? Something like that. Okay, so Earth, and this is the atmosphere. So, when the sun is directly overhead, okay, and the light's trying to reach you, okay. So what you notice is that, of course, the blue scatters the most, right? And other colors scatter too, but it's the blue that scatters the most. In fact, that begs the question that why is the sky not violet? Anyone knows why? I mean, violet is a factor about, two more, as you go into the far ultraviolet. Well, I mean, so one of the reasons is that your eye is just not, in fact, the main reason is that your eye is not sensitive to violet. Its sensitivity is actually peaked in the yellow. And, but, you know, so your eye is not sensitive. That's why you don't see violet. Otherwise, the sky is violet, actually. So anyway, you see the blue, right? So this is your blue sky. Now, an interesting thing happens when the sun is now past the horizon. So I mean, like now it's somewhere here. And all that's changed is that now to get to you, it has to travel through a longer distance. This distance is longer than when it was directly overhead. And just that small change is enough to cause something interesting, that now the blue is scattering furiously, and it all scatters away by the time it can reach you. So there's hardly any blue left. It's all scattered away. And so what gets to you is the part that does not scatter much, which is the red. And so that's why it does not scatter much, so it stays localized near the sun. It doesn't just spread all over, but that's why you see the pink sunset. So it's all it was is just a slightly longer path. And we had a demo actually for this, and but there's no way that it would show up in our current arrangement, because it needed you to look at it from different angles, and it happens kind of fast. So there's no way to show it. Okay, so in any case, so I hope that that was a clear explanation for the blue sky and the pink sunset. Are there any questions about? And please note that this was a good model for Rayleigh, for the Lorentz model, and Rayleigh scattering. We did not talk about Mie scattering, which is a more complicated topic. Okay. Any questions so far?
So why are sunsets, like the colors enhanced when there's like volcanic eruption and there's a lot of fine particulate?
Okay. Now that's an excellent question. So besides the air, now you have a lot other scatterers, and one thing is that I imagine that those scatterers are much larger, and so there may be Mie scattering going on also. In which case, all the frequencies are scattered equally. Now, if there's just a lot more blue around, then the blue will maybe get scattered more. And also, I can imagine that the red, which is all that's left, is also then carried further out. Like, I mean, there's more scattering of that because there's simply more scatter particles around that will scatter anything. Like any frequencies they can see, they will scatter. And so the reds can get exaggerated just because there's more scatterers there, and it gets spread out more. And I'm sure that there are finer particles also. Well, I don't think volcanic eruptions would ever give you particles that are as fine as air. Has anyone ever seen the inside of a glacier? Like, I mean, when a glacier shears off, and would you be familiar with if I said that when a glacier freshly calves, and breaks off, then the inside of the glacier is brilliant blue. Are you familiar with what I'm saying?
Yes.
And that's for the same reason. What happens is that as the glacier forms, there's huge pressure because of layers and layers and layers of ice that just, and also what happens is that the water freezes first to become ice, and air bubbles get trapped because air is dissolved in the water, but when the water becomes that cold, air comes out of solution, and so you have these air bubbles. But the interesting thing is that the ice sheets get compressed more and more and more and more and more, and because of that compression, air starts to come out of solution from the water. And anyway, so there are these really fine micro bubbles, which are as small as air particles. And so it's like dense air scatterer. I mean, it's like dense scatterers inside that material. And so now when it gets exposed, then it's because of those fine micro bubbles scattering and rally scattering, and you see blue. It's a brilliant blue. In fact, if you go inside really dense glaciers, and sometimes there are these tunnels and caves and inside a glacier, and things appear violet there because there's enough of this scattering in a closed volume, that you can actually see violet. And it's pretty amazing. I'm not sure how I started talking about the glacier. Maybe from the volcanic stuff. Any other questions? So this actually, concludes a theme that I was trying to. Oh, and there's one other thing. There's one other success. And this success is that why do things appear green underwater? And actually this brings about this is an amazing fact about water in general. I want to show you a graph and what I'm going to do is, this is from Jackson. It's one of the things my professor in E&M in grad school really got all excited about, and I can see why. So I'm going to actually call this the magical, absorption property of water. I'll tell you this, that and of course none of us will, but if you ever had to make an argument for intelligent design, this would have to be it. And of course none of us believe in it, and I'm assuming because we're scientists. But if you had to make that argument, this would have to be it. Because look at the magical absorption curve for water. I want to draw to your attention that on the x-axis it's frequency. Okay, and this is a huge scale. That's 10 squared hertz, 100 hertz, going out to 10 to the 22. So this is like gamma ray territory here, and these are like, cosmic waves. I'm not sure how to, I mean, like, if you were to use c equals nu lambda, then the lambda for this would be kilometers, hundreds of kilometers, you know. And gamma rays, of course, then it's like, uh, uh, fraction of nanometers. So this is a huge, like, that's the wavelength, but this is frequency, okay? And on the y-axis, there's absorption. And what I want you to notice is that if you look at the curve for water, okay, so it's something like this, and I mean the absorption varies widely, but it is significant, for almost the entire frequency range. And look how it peaks here, and it does all this number, and here it's like here at this top it's 10 to the 4 units, 10 to the 4 per centimeter. Remember that attenuation, that absorption coefficient, 10 to the 4 per centimeter, meaning just over 1 centimeter of propagation, the intensity absorbed is 10,000, and all you're left with is 1/10,000th of the intensity right there. But then it comes back down, And by the way, this 10,000, where does that happen? That happens right where you make your microwaves. So right here, 10 to the 12 hertz and all, that's your microwave. That's why that technology works so well, because water absorbs a lot at that frequency. But then look what happens. It then dips down, all the way down, all the way down, all the way down. Okay, by how much? By 10 to the 4 down to 10 to the minus 4. 8 orders of magnitude. And over what range does the absorption dip? Just between, if you can see this, there is a line here. This very, very narrow frequency range. Extremely narrow frequency range. I've drawn a red line and a green line. That's the green line, that's the red line. Okay? And in this region it dips down, but then it shoots right back up again. Look how high it goes. This is the violet part. Well, I think you're seeing now what I'm saying. This narrow window, this is the visible window, the visible frequencies. Your eye can see within this extremely narrow window this huge frequency scale. Okay? So Jackson, and so there is a handout that I give out with this, and it says here, to quote J.D. Jackson, physics, who writes that book, he says, the reader may meditate on the fundamental question of biological evolution on this water-soaked planet, of why animal eyes see the spectrum from red to violet, and of why the grass is green. Mother Nature has certainly exploited her window. Look at what a narrow window nature had, and all the colors that we see, and life depends on all these things that our eyes see. It's all within this extremely narrow window. Isn't that amazing? Otherwise, water is highly absorbing everywhere outside. It's a highly absorbing thing. It's opaque. You can't see through it. It's highly absorbing. Therefore, it's it's hard for electromagnetic waves to propagate through the air if the air is humid. That's why radar and all this. I think right here that's the radar. That was a huge problem in World War I, that radar used to get absorbed, and so they had to come up with other ways to detect. But anyway, water is highly absorbing, except for this narrow window. Okay, and in fact, now if you ask why do things appear green underwater, well, because as you go from red to green, so I've actually color coded it just right. So this is your Roy div or whatever, right? It's all within this narrow window. And but if you look at the absorption, okay, so what happens is that let me just find that page that yeah. So if I magnify this part out, you know, so this, let me just magnify it. So here you have uh, red, and here you have, let's say, blue. Okay, and on the y-axis you have absorption. Then what's happening is that this this absorption curve, it's not like it was very high here, you know. So it's not like it was very high here and then it just goes down to zero and then it comes back up. It's not like that. You'll notice that there's a gradation, there's a function to it. So it actually falls off gradually like this, and then it comes back up. Okay, and so what you see is that the reds, as it goes down to zero, you see in here, this part, that reds are preferentially absorbed. Okay, compared to greens. And that's why when you're underwater, things appear green. Because the reds get absorbed out, the greens and the blues are sort of allowed to, they don't get absorbed as much. Okay? So that's the reason. But this is an amazing graph. Like, I mean, if you look at it, this extremely narrow window that happens. And all the colors that we see and everything, and the relation of water to that, because oftentimes, the air gets very humid and everything. And if this absorption had not dipped to near zero, if it were still as high as it is, like if this curve is, then we would not have been able to see through humid air. And that's an amazing thought. But that kind of finishes this theme of things that one can understand from the Lorentz model. And now there's only two topics left to discuss. One is the issue of line widths, because that ties in. I mean, and both these topics have to do with the lab that is that I have to put up the videos and that you will be studying basically this week. So both these topics have to do with that. I mean, one is this issue of line widths, because that's what you measure in the lab, the narrowest line widths that you can see. And the other issue is that of, well, the hyperfine structure of the atom, the spin of the nucleus. So how does saturated absorption spectroscopy work? Let me pause the recording for now. I've been talking for 53 minutes. I hate that, actually, because I've been talking for far too long.